In this class, let us learn what is chromatic polynomial. A given graph G of n vertices can be properly colored in many different ways using sufficiently many number of colors. Okay. This property of a graph can be expressed by using a polynomial, and that polynomial is nothing but chromatic polynomial, and it is denoted by, say, Pn of lambda. I'm using lambda colors, and graph G has n vertices. This is the notation. There are many ways of denoting chromatic polynomial. I'm using this notation. The value of the chromatic polynomial of a graph with n vertices gives me number of different ways of properly coloring the graph using lambda or fewer lambda colors. Okay, at the most lambda colors or less than this. Value of the chromatic polynomial gives me number of different ways of properly coloring the graph G, which has n vertices. Now suppose, how is this expression? How is the expression for Pn of lambda? Let us look at it. Suppose I have to choose I colors out of lambda colors. Okay, how many different ways I can do it? I can do it in lambda c ways, ci ways, that is same as writing lambda ci, which is nothing but lambda factorial divided by lambda minus I factorial into I factorial. I'm not using this notation, I use this. I hope you know NCR, NPR formula. Same formula I have used. Choosing I colors out of lambda colors can be done in these many ways, these many different ways. I'm using this notation. Okay, let Ci, this is different Ci, let Ci be the different ways of properly coloring G using I colors. Properly coloring G using exactly I colors. I different colors, in fact. Now we can choose I colors out of lambda colors in these many ways, right? Therefore, I can write, therefore G can be properly colored using I colors in Ci into lambda Ci ways. Since I can be any positive number, positive integer which varies from 1 to n, therefore I can write Pn of lambda as summation I ranging from 1 to n is number of vertices in the graph G, is Ci into lambda I, which is nothing but, which can be written as Pn of lambda equal to C1 into lambda 1 C2 into lambda C2. It's NCR formula, okay? Don't get confused with this Ci with this lambda n, which is nothing but C1 into lambda factorial divided by lambda minus 1 factorial into 1 factorial plus C2 into lambda factorial divided by lambda minus 2 factorial into 2 factorial dash 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 cn into lambda factorial divided by lambda minus n factorial to n factorial, which can be written as c1 into lambda plus c2 into lambda minus 1 by 2 dash dash cn into lambda minus 1 lambda minus 2 lambda minus n minus 1, that will become plus 1, divided by n factorial. Okay, this is the general formula. I'm coloring graph G with n vertices using lambda colors. In how many ways I can do is this. See, here these C1, C2, Ci's depends on the graph. Suppose I have a graph which contains only one edge. Suppose, okay, my graph is this single edge. It has got two vertices. Now how many minimum colors I need to properly color this is 2, right? Minimum number of colors for proper coloring of this graph is 2. If I give green here, then say blue over here, right? So in this case I need minimum 2 colors. Therefore, using one coloring of this graph is not possible. Therefore, when I take this graph, C1 value is 0 because I need minimum 2 colors. What is Ci? Ci is number of ways graph can be colored. Number of ways graph can be colored with given I colors. Okay, so using one coloring is not possible. Proper coloring is not possible for this graph. So I need minimum 2 colors. Therefore, for this graph, C1 is equal to 0. Suppose my graph has got a triangle. Okay, say cycle of 3H. Now in this case, I need minimum 3 colors for proper coloring. Right, here I gave orange, say black, red. I need minimum 3 colors. Therefore, for this graph, C1, using one color, proper coloring is not possible for this graph, so C1 is 0. And even using 2 colors also, I cannot properly color this graph. So therefore, C2 is equal to 0. So therefore, I can say if graph with n vertices, if I have graph with n vertices, using n different colors, I can properly color the graph by, in fact, n factorial ways I can color. If I have a graph G with n vertices, and by using n different colors, I can properly color this graph in n factorial ways. Therefore, I can write Cn is equal to n factorial. You can check this here. N here is 3. It is 3. So Cn is, that is C3 in this case, which is nothing but 3 factorial ways, which is nothing but the value is 6. This is one way. Then I can exchange these two so that I'll give one more like that. I can exchange these two like this. So OBR, I can give BR O, that is one combination. Then I can give R B O, like that. I can change many ways, right? So there are 6 ways for proper coloring of this graph with 3 colors. So now let us look at what is the chromatic polynomial for a complete graph or for a tree and all. Okay, so usually graph will be given to you and you have to find the chromatic polynomial for the graph. So first thing is you have to check whether it is a complete graph or it is a tree. Okay, so there is a theorem for a complete graph which gives you the chromatic polynomial for complete graph, and there is a standard expression for tree, chromatic polynomial for tree. So now theorem says a graph of n vertices, it will be a complete graph if and only if its chromatic polynomial is like this. See, when I have a complete graph, I'll just explain this. This is the complete graph. Okay, I have lambda colors. Okay, for coloring this vertex, I have got lambda options. Since I have lambda colors, first vertex, I have got lambda options. But when I come to this vertex, second vertex, I cannot give the same color which I have given over here. So one option is less, therefore I have got lambda minus 1 option for coloring of this vertex. And when I come to this vertex, I cannot give the same color which is given over here, and even this color I cannot give. So two options are less, so I can color this vertex using lambda minus 2 options. I have got lambda minus 2 options. And when I come here for this vertex, I cannot give this color, cannot give this, cannot give this. So 3 out of lambda I have to remove 3 options. So I have got lambda minus 3 options for proper coloring of this vertex, right? So overall for this graph, chromatic polynomial will be lambda into lambda minus 1 into lambda minus 2 into lambda minus 3. Okay, so this is the complete graph on 4 vertices. In general, this is how it works. Okay, so now what I have to do is I'll choose a vertex V and color it with any one of lambda colors. Okay, vertex V, color it with any one of lambda colors. In how many ways I can do? I can do it in lambda ways. In lambda ways means giving one color, second color, third color, like that. So there are lambda options. Similarly, a second vertex, when I consider, that can be properly colored. Second vertex can be properly colored in lambda minus 1 ways, right? Like that, the third vertex, that can be colored in lambda minus 2 ways. Like that, nth vertex, when I come, nth vertex, that can be colored in lambda minus n minus 1 ways. This is possible, this way of coloring is possible if and only if every vertex is adjacent to every other vertex. Got the point? Therefore, that is same as writing this proper coloring is possible if and only if graph is complete. That is, this is possible if and only if the graph is complete. Okay, in fact, all the vertices that can be colored in lambda into lambda minus 1 into lambda minus 2 dash dash lambda minus n plus 1 ways if and only if the graph is complete. All the vertices can be colored in lambda into lambda minus 1 lambda minus 2 dash dash lambda minus n plus 1 ways. This is possible if and only if the graph is complete. So that chromatic polynomial will be lambda into lambda minus 1 lambda minus 2 dash dash lambda minus n plus 1. This is for complete graph. Next, let us look at chromatic polynomial of a tree. If you have tree on n vertices, then its chromatic polynomial is Pn of lambda equal to lambda into lambda minus 1 power n minus 1. I'm using induction on number of vertices to prove this expression. Okay. Proof by induction. Induction on number of vertices, that is n. So when n equal to 1, that is isolated vertex. For an isolated vertex, Pn of lambda, that is P1 of lambda, which is equal to simply lambda. When n equal to 1, it is 1 minus 1, 0, lambda minus 1 power 0, so it is lambda. Then that is same as writing, we can color the vertex with lambda colors. So when n equal to 2, Pn of lambda, that is P2 of lambda, is lambda into lambda minus 1 power 2 minus 1, which is nothing but lambda into lambda minus 1. That is, we can color two vertices in lambda into lambda minus 1 ways. So I'll assume this result is true for all the trees with the number of vertices, say, less than or equal to k. Assume the result is true for all the trees with the number of vertices is less than or equal to, say, some k. Okay, so the graph can be colored in pk of lambda. When I consider, that will be lambda into lambda minus 1 power k minus 1. Now consider a tree with k plus 1 vertices. Consider a tree with k plus 1 vertice. We know that every tree with n greater than or equal to 2 has minimum 2 pendant vertices. Right? Every tree has minimum 2 pendant vertices. So removing one of them along with the edge, we are left with the tree which has got k vertices. Say this is the tree, suppose, say some tree. Totally I take, there are minimum 2 pendant vertex if I consider. And if I remove one pendant vertex along with the edge, totally there were k plus 1 vertices. When I remove one such pendant vertex along with an edge, I'll be left with the tree which has got only k vertices, right? So by inductive hypothesis, this graph with k vertices can be colored in lambda into lambda minus k minus 1 ways, right, after removing one pendant vertex. Now after coloring all these vertices, I'll attach the pendant vertex along with the edge. So what happens? Now this pendant vertex, when I attach, I cannot give the color which is already assigned to this vertex, right? So the pendant vertex can be colored in lambda minus 1 ways. Thus, all the vertices can be colored in lambda into lambda minus 1 power k minus 1, and this last pendant vertex which can be colored in lambda minus 1 ways. So that will give me lambda into lambda minus 1 power k ways for proper coloring of graph with k plus 1 vertices, hence the proof. I repeat, initially I'll take number of vertices as 1 and I'll get Pn of lambda equal to lambda. When I take n equal to 2, I'm getting lambda into lambda minus 1. I'll assume that the result is true for all the trees which has got k vertices. So that Pn of lambda is this. Now I'll take a graph tree with k plus 1 vertices. I know tree will have at least 2 pendant vertices. What I do is, in my tree, I'll remove one pendant vertex along with the edge associated with that, so that my graph, my tree, will contain only k vertices. We have already assumed for a tree with k vertices, Pn of lambda is lambda into lambda minus 1 power k minus 1. Okay, so now after coloring all these k vertices, I'll add that pendant vertex now along with the edge to the same position from where I have removed. Okay, so now I have used k colors for these. Now this one particular pendant vertex, I can color it in lambda minus 1 ways, because I cannot color it with the same color which I have given over here, right? I have used lambda colors. One color is already used here, that cannot be given for this vertex. So this vertex will have lambda minus 1 option, so that total k plus 1 vertices in my tree, I can color it in lambda into lambda minus k power minus 1. This is without pendant vertex. After adding a pendant vertex, that have got lambda minus 1 option, so I am multiplying it, so that Pn of lambda for a tree is lambda into lambda minus 1 power k if I have n equal to k plus 1. So this is by, proof is by induction on number of vertices. Let us look at few examples. I have few graphs here. We'll tell you how to write the chromatic polynomial for the graph. So when the graph is given to you, you have to check whether it is complete graph or a tree. So for these two graphs, I have a standard formula. So first graph is tree. Okay, it's tree on 1, 2, 3, 4, 5 vertices, right? So for a tree, Pn of lambda is lambda into lambda minus 1 power n minus 1. So here I have 5 vertices. So Pn of lambda is lambda into lambda minus 1 power 5 minus 1, so that it is lambda into lambda minus 1 power 4. This is one way. Other way is I'm coloring this with lambda colors. So this vertex has got lambda options, lambda colors to put. When I come to this vertex, I cannot color it with the same color which I have used for this. So this has got lambda minus 1 option. Similarly, this vertex, I cannot give the same color which is given to this. So this again has got lambda minus 1 option. Like that, this I can give these colors I can give to this, but I cannot give this. So only one option is less, therefore lambda minus 1 option. And even for this, I have got lambda minus 1 option. So in total, Pn of lambda is lambda into lambda minus 1 into lambda minus 1 into lambda minus 1 into lambda minus 1. That is lambda into lambda minus 1 power 4. This is other way. This is using the formula. For this tree, 1, 2, 3, 4, 5, 6, 7 vertices are there. So Pn of lambda, see, this can be colored in lambda ways. Lambda colors can be given to this vertex. For this, one less than this, because I cannot give the same color of this. So this has got one less option. Even this, when I come to this again has got one less, because I cannot give the same color. These two should not be same. So this vertex has got lambda minus 1 option. But when I come to this vertex, I cannot give the same color of this, but I can give this color. So this is again has got lambda minus 1 option, lambda minus 1 option, lambda minus 1 option. So in total, 1, 2, 3, 4, 5, 6 lambda into lambda minus 1 power 6. You can apply the formula also. N is 1, 2, 3, 4, 5, 6, 7. Lambda into lambda minus 1 power 7 minus 1, that is 6. Okay. Now for this graph, complete graph on 4 vertices. For a complete graph, Pn of lambda is lambda into lambda minus 1 into lambda minus 2 dash dash up to lambda minus n plus 1. This is for complete graph. We have the standard formula. Here in this case, n is 4. So P4 of lambda is lambda into lambda minus 1, lambda minus 2, lambda minus 3. See, this has got lambda option, and I have explained this example, I guess. Yeah, the same example I have given can be colored in lambda ways, lambda minus 1 options, lambda minus 2 option, lambda minus 3 options. So Pn of lambda is lambda into lambda minus 1 into lambda minus 2 into lambda minus 3. You have two more graphs. This is not a complete graph, general graph on 4 vertices. What is the chromatic polynomial for this graph? See, this vertex, if I give, I can color it in lambda ways. When I come to this vertex, I cannot give the same color which I have used this. So this has got lambda minus 1 option. And when I come to this, I cannot give this color. Same way I cannot give this color. So this has got 2 options less. So lambda minus 2. When I come to this vertex, I cannot give the color which I have used over here and over here. So 2 options I cannot give. So this is again lambda minus 2. So in total you can write lambda into lambda minus 1 into lambda minus 2 square. The other way, you can use the formula I equal to 1 to n ci lambda I. This formula you can use. Here n is 4, so summation I ranging from 1 to 4 ci lambda I, which is same as writing c1 lambda 1 plus c2 lambda 2 c3 lambda 3. So I have to evaluate c1, c2, c3, c4. Now c1 is nothing but number of ways of coloring using one color. So that is not possible. Therefore c1 will be 0. For this graph c1 is 0. And using two colors, I cannot color it with two colors. So c2 is 0. Coloring means proper coloring, okay? So c2 will be 0. And I have to evaluate c3 and c4. I know for a graph on n vertices using n colors can be done in n factorial ways. So c4 is 4 factorial. Just thing is I have to evaluate c3. What is that? For c3, 3 colors can be assigned to 3 vertices. Say it has got a triangle, 2 triangles are there. So 3 colors I am giving first color, second color and third color. This is one option, right? So 3 colors can be properly assigned to 3 vertices in 3 factorial ways. So when I give these 3 different colors to these 3 vertices, now this vertex has got only one option, that is coloring it with the same color of this, right? Say this is v1, v2, v3 if I consider. Now v1, v2, v3, I have used 3 different colors for these 3 vertices. Then this color has got only one option, right? So that is color it with the same color as of v2. So c3 will be equal to 3 factorial, which is nothing but 6. Therefore, when I come to Pn of lambda, this will be c1 is 0, c2 is 0, c3 is 6, lambda 3 it's nothing but lambda into lambda minus 1, or I can write lambda factorial divided by lambda minus 3 factorial into 3 factorial plus c4 is 4 factorial, lambda factorial divided by lambda minus 4 factorial into 4 factorial. So that gives me this 3 factorial and 6 will get cancelled. I'll be left with lambda into lambda minus 1 into lambda minus 2 over here. And here this 4 factorial will get cancelled. I'll be left with lambda into lambda minus 1, lambda minus 2 and lambda minus 3. Take out lambda minus 1, lambda minus 2 outside. Inside the bracket here 1 plus lambda minus 3. So that lambda into lambda minus 1, lambda minus 2, lambda minus 2, which is nothing but lambda into lambda minus 1, lambda minus 2 to the power 2. That is same as lambda into lambda minus 1 into lambda minus 2 to the power 2. Same manner for this graph, see c1 will be 0. I cannot color it with one color. Similarly with two color I cannot give. c2 is 0 and I know c5 is 5 factorial. To get c3, the same as this, I have a triangle everywhere. So when I color 3 colors for these 3 vertices, then these two will have only one option, that is I can color it with the color of this this vertex is colored with the color of this, and this vertex is colored with the vertex or color of this vertex. So when I color these three, these two will carry only one option each. Therefore, C3 is nothing but 3 factorial. Okay, and to get C4, I have 4 colors and I'm coloring say V1, V2, V3 and V4. So coloring these 4 vertices can with 4 colors can be done in 4 into 6 ways, that is in 24 ways. Only these 4 colors for these 4 vertices can be colored in 24 ways. The fourth color can be assigned either to the vertex V4 or to the vertex V5. In the sense, this vertex and these two vertices, the fourth color, I can give it to this or to this, right? 2 choices I have. So that is 24 into 1 plus 24 into 1. So C4 will be 48. So put these values C1, C2, C3, C4 and C5. Pn of lambda you are getting as lambda into lambda minus 1, lambda minus 2 into lambda square minus 5 lambda plus 7. Put it in this main equation. Okay, here you have got 5 vertices, so summation I from 1 to 5 you have to take and put the values of C1, C2, C3, C4 and C5. Okay, this on simplification you are getting this expression for this graph.